Why don't we go ahead and get started? So welcome back everybody to E290C. For those guys who are here in person, for the handout, don't worry, it's not lecture 18 just yet. I didn't skip 17 lectures. It's just a minor typo. This is lecture number 2. So last time we just sort of kind of gave global introduction on why this class is hopefully going to be interesting and what's going to be fun and challenging about it. So today we'll actually start diving into the material. I haven't actually posted the homework and stuff up yet. I'll probably do that early next week. So just be out on the lookout for that. Hopefully by the end of today, actually, you'll know a reasonable amount of kind of what you need to do for that first homework. But like I said, just be on the lookout for that. So before I get going, any other questions from last time or administrative kind of stuff we should go over? All right, good. So for today, what I'm mostly going to do is kind of give you a little bit more of, let's say, an overview of what high-speed links are sort of about and kind of what some of the issues you need to worry about. But most of the lecture I'll actually focus on actually taking a look at, what are those things that we actually do the signaling over, meaning kind of what is the environment that you're going to be operating in, and what are the few of the things you really need to worry about in terms of how that would impact the designs that you'd end up doing. And this will really be just sort of a glimpse at things, because as you'll see, turns out it's actually a pretty complicated field in terms of figuring out, exactly what's causing all of the different types of issues that you're facing. Because you'll see it's a fairly actually complex physical system. And so obviously there's lots of different components you could be playing around with. But as I said, the kind of goal of today is really just to give you an idea of what are the things you need to care about and why they end up the way they do. Okay? So to start out with, I kind of wanted to just go back to that picture of what the most basic link actually looks like. Because as we'll see, it's going to be sort of useful just to sort of highlight a few very basic issues that I wanted to make sure everyone is on the same page on. So as I kind of said last time, you could kind of imagine a link as just being sort of like a flip-flop, an inverter, some wire, another inverter, another flip-flop. I've redrawn that a little bit here, let's say slightly more conceptually and at the same time slightly more detailed. So I've just replaced sort of one side with, I've called it just a transmitter for now, and we'll come back actually next lecture and talk a lot more about what you'd really put inside of that thing. And then on the receive side, I've basically just put a comparator with a clock. Okay, now I've put a comparator with a clock because for now I'm basically going to assume that we're really just talking about essentially binary signals, meaning it's either a 0 or a 1. And so if you want to know what the bit is, you just have to decide, is it essentially greater than some threshold or lower than some threshold? And of course, to do that, you basically do that with a comparator. Okay, so again, we'll actually talk a lot more about kind of what goes inside of this box actually next lecture. But that's just sort of, from 30,000 feet to make sure we're on the same page. Okay, so the first thing I wanted to just, briefly mention, which is a little bit of a review from 240, but, we'll spend a little bit of time on maybe other things you haven't heard about before, is just keep in mind that your goal in building a link, or really any communication system, is basically to get the same information from the transmitter to the receiver, right? So in other words, if you get the different information at the receiver and you don't sort of figure out that you actually got different information, bad news, right? So, of course, as soon as I say that, the question is, well, why wouldn't you actually just get whatever you sent, right? So, all right, well, why wouldn't you get what you sent? What problems can you guys think of that would cause it so that what you actually sent at the transmitter is not what you actually receive at the receiver? So what do you guys think? Okay, so the first one, I guess, as even just a guess from having taken 240, you can always sort of say noise, right? In 240, everything was, if I asked you something, half of the time the answer was there's some noise problem. Okay, so that's clearly the case. So we'll talk some more about that in 1 second. But before we sort of, let's maybe do a little bit more detail on that. So what does noise really mean? Or rather, how does noise maybe manifest itself in terms of what the problems we will see are? Why does noise matter? And when you say noise, like what kind of noise do you even mean?
Noise at the receiver is when it's as large or comparable to the amplitude of the signal.
Okay, so you said something about noise at the receiver and something about it being comparable to the signal, right? So that's absolutely correct, and we'll draw something maybe a little bit more detailed, but in some senses what you're kind of saying is if I'm sending voltage and I'm receiving voltage, then I want my voltage noise to be small in comparison to the amplitude of the voltage signal. Okay, that's absolutely correct. Anything else? Any other kind of noise you can think about?
Noise on your timing.
Yeah, there we go. So it turns out, unfortunately, not only can you have noise on your voltage, or whatever your physical, let's say, quantity is. You can also, of course, have noise on your timing. Okay? So we'll draw a picture in one more second, but you can imagine that, if you don't actually check the values of the bits at the right time, you'll get the wrong answer, right? So we'll actually draw a picture for that in a second. What else might actually matter? What other kinds of things can sort of mess you up and make it so you get the wrong bits on the other side?
ISI.
Okay, you said ISI. We'll come back to that one in 1 second. Oh, you're going to say the same thing. Okay, so what does ISI even stand for?
Inter-symbol interference.
Okay, yes, you said it's inter-symbol interference. So I want to just slightly generalize. So what's bad about inter-symbol interference? Like, what does it sort of do that makes you get the wrong bits?
Your RC delay.
RC delay.
Your channel's like a low-pass filter, so
Okay.
when you have a change, it sort of smears it out, and then it can
Okay.
interfere with
So what you said was, let's say I have a low-pass filter in my channel. By the way, it doesn't have to be low-pass. We'll see all kinds of fun channels in a second, but generally it is low-pass. Okay, so what you kind of said was, well, if what I sent was something nice and clean like this, then by the time I get it at the end, it'll be some smeared out, weird-looking thing like this. Okay, that's absolutely correct. So I want to just generalize that slightly and call it distortion. Okay? Because it turns out you could actually have nonlinear channels. You could have all kinds, your circuitry could be nonlinear, right? You can have all kinds of weird stuff happening that would just distort your signal. Okay, so in some senses, inter-symbol interference is a form of distortion. Okay, so that's certainly an issue. All right, anything else you guys can come up with?
Dispersion.
Yeah, so dispersion I would kind of claim is kind of like distortion in the sense that, it's somehow taking your signal and filtering it. Right, or it's sort of changing its shape and making it look weird and not the way you wanted it to be. That you're absolutely correct. It just I'm going to categorize that under distortion.
Reflections due to domination impedances.
Okay, so that's true, and we'll actually spend a lot of time talking about that today. But I'll still claim that that's probably in the context of distortion. Or well, there's another piece that you could have said, but yeah, go ahead.
Interference.
There we go, interference. So what do you mean by interference?
So, you have several links that are probably on the same chip or whatever, very closely located. And if they have a high enough signal, they're going to couple.
There we go. So actually, it doesn't have necessarily to do with the size of the signal in terms of how much they couple. Usually that's more, let's say, of a physical thing in terms of, let's say, the coupling ratio. But certainly how much problem it will cause is strongly dependent upon the amplitudes of the signals, right? So interference actually is a pretty big deal. Now, for those of you guys who are wireless people, the good news, or maybe the bad news is, interference is not as big of a deal in links as it is in wireless. That's one of the nice things about having a wire there and not, just blasting stuff out into space. But it is actually still a pretty big issue. Okay, and by the way, interference, we've mostly been talking about other signals so far. But by the way, it doesn't necessarily just have to be that. Your power supply could be moving. I don't know, the lights could be flickering. Just about anything can actually come and essentially cause interference. Okay, now, just to be sort of really clear, usually when people say noise and interference, they actually sort of sometimes use them interchangeably. And I will probably do the same thing as well. Okay, but from a, let's say, technical standpoint, and especially if you look at most of, let's say, the definitions of people looking at signal integrity or sort of doing performance modeling, noise really means fundamental things that are random and you can't control. Okay, meaning you can't predict what the value actually is. It only has statistical distributions associated with it. Interference, in theory, if you knew the entire world, you could predict. Okay, so interference is more of a deterministic effect. Nonetheless, you still often end up modeling it as being statistical just because the world is complicated and you don't want to have to know every single last detail about every single last thing in the planet. Okay? So that is indeed kind of, I think, the three main categories. If somebody can come up with another one, I'd be very interested. But I think this is probably the three main sort of categories that you really need to worry about. So the only other thing I want to do is just sort of draw a little bit of a picture, in particular in terms of the noise, because it'll sort of help us on the next slide as to why you'd actually care about that. So what we've kind of been saying is that, if I go back over here, if I say that I'm transmitting some voltage in my transmitter and I receive some voltage on my receiver, and then I look at sort of also this clock, what we're basically kind of saying is that, and I'll just erase this little dispersion thing over here. What I'm basically saying is that if I looked at, my transmitter, and let's say I sent something like this, well, okay, it may take some time to actually get over to the receiver. So ideally speaking, I should get something like that over at the receiver, right? And let me just label that VRX. Okay, well, so what we're really now saying about this sort of voltage noise is, kind of as we said before, we just want to make sure that, if there is some noise on this signal, and in particular, in an example, I'll just draw some stuff here. Well, maybe I got really unlucky and there was a huge amount of noise and something like that happens, right? So even though I tried to send a 1, the noise was big enough that I just stayed below that voltage threshold, right? So clearly that's an error, right? Okay, and so that's, as we were kind of saying before, that really tells you that what you end up caring about is kind of how big the signal is relative to that noise. Okay, and we'll actually go into that in more detail in 1 second. Again, for those of you guys who took 240, you know a lot about sort of, or 240 with me, I should say, you know a lot about kind of why that matters, okay? The other piece, which we talked a little bit about in 240, but not as much, is that, as we sort of highlighted up over there, you actually care not just about, let's say, voltage noise, but even about timing noise, okay? So ideally speaking, if I had sent that, bit over at that time, I want to make sure I put my clock in a region where I definitely got that particular bit, right? Because if I shift my clock over into different regions, then I'm actually going to get different bits, right? So if I sort of draw, let's say, an ideal clock waveform like this, where this is good, well, just like I can get noise on my voltage, well, guess what? Due to some weird noise event somewhere, my clock could show up at the wrong time, right? And if my drawing was a little bit better, so that I didn't have to angle that thing, I would have made it really clear that that jittered clock or that timing error caused you to actually sample the wrong bit. And then if my next clock came around over here, right, I just completely missed that bit that you were trying to catch, right? Does this make sense to everybody? Or? Okay, now, by the way, why is there noise in time? Like, why is there this, jitter on the clock? What's the cause of that?
There's like amplitude to phase conversion.
Okay, so
like,
there's amplitude to phase conversion. What do you mean by that?
So if you have like voltage noise and like say you have a transition on your signal, then that ambiguity in your amplitude causes time.
There we go, exactly. So to state what you're saying in another way, any of my timing signals are fundamentally a voltage, right? So if I put noise on that voltage, then fundamentally there's uncertainty in time as well, right? Because the only way I can sort of tell what time it is based on some voltage signal, okay? So it's really kind of the same thing. It's just that timing sometimes tend to be, let's say, a little bit more confusing because the way it really ends up causing errors is a slightly different mechanism than just this directly voltage noise of pushing you, in voltage into the wrong place, okay? So actually later on we'll talk a lot more about how you can actually sort of, let's say, more rigorously deal with both of these effects. But for now, just keep in mind, both of these really do actually matter, okay? So one sort of nice way of thinking about this, or I should say really characterizing all this, is what's called the I diagram. And again, I think many of you should be familiar with this, but just in case you haven't seen it in a while, or you didn't take 240 with me, let's just kind of quickly walk through that. So what an I diagram really is just saying, if I take whatever voltage signal it is that, for example, I'm either transmitting or receiving, in this particular example, or most of this class, we're going to be focusing again on these sort of binary types of things, right? So there's just 2 levels there, okay? So if there's only 2 levels, then what I can kind of do is, okay, well, if I send some low level and some high level, and, okay, there's maybe some transition time, what I can kind of do is characterize how much, let's say, space there is between the low level and the high level, and how much time I have to actually correctly capture that particular bit, okay? So as an example, if I just sort of took, let's say, an arbitrary number of those bits, and instead of just looking at it, over all time, I kind of always looked at everything modulo 1 bit time, right? So I kind of like take the waveforms and put them all on top of each other, right? Well, if I kind of do that, then what you can imagine is if I have things that I've sent that look like that, well, when I put everything on top of each other, I should just get some sort of pattern that looks like this. Okay, now maybe you can see why it's called an I diagram, just because, I don't know, that looks like a squinty eye. I don't know who originally came up with it, but that's kind of where it came from. Okay? So the idea here is that what you want to do is figure out okay, how much sort of voltage do you have inside of this eye? Because that indicates that, anywhere inside of there you're kind of good, right? And how much, again, time do you have inside of that eye? Because, again, any sort of sampling point inside of there for something at least that looks like this would also be good, right? Now, of course, if I put noise on the voltage, then what I'm basically doing is I'm moving around that height of the eye, right? I'm kind of putting different lines on here than what I nominally wanted. Similarly, if I have noise in time, or jitter, then I'm sort of shifting around where that actual transition occurred, right? So of course, if I have both of these things, you end up with something that looks like that, right? So it's not exactly clear when the transition in time happened. By the way, this is just sort of an oscilloscope trace with infinite persistence turned on. So the way you sort of interpret this is something that's, let's say, a more yellow or white color means that you've sort of, there isn't as much voltage points there. And something that's darker means that there's a lot of voltage traces that, took that particular trajectory, okay? So what this is kind of saying is, of course, if the thing's jumping around a little bit, then you have some traces over there. But if there's no, you don't see anything, that means that you never actually got into that spot, okay? And in terms of signaling, the more this white space is, the better, right? Because that means that you have very, very clean transitions, both in terms of the voltage and in terms of the time, okay? Make sense to everybody? Or? Okay, great. So, again, just sort of quick review from, I think, what hopefully most of you guys have seen before. So, like I said, our goal was actually to get the same bits from the transmitter over to the receiver, okay? So, turns out, because there's always noise in the world, there's no way you can guarantee that over all possible time in all possible scenarios forever you will always get exactly the same bits, because thermal noise, just one day somebody could decide that you have a 10 megavolt noise signal and sorry, you didn't actually transmit 10 megavolts, so no way you're bigger than that, okay? It's obviously very unlikely, but could happen, okay? So what you always end up having to do is essentially characterize, okay, well, I can't really make it so that I never have an error, but let's see how long or how many bits I can send and sort of be confident that I didn't get any error during those bits, okay? So the way you characterize that is, of course, what's called the bit error rate. And that's really just the average number of incorrectly received bits divided by the total number of transmitted bits, okay? And so just as an example, if we were, let's say, looking at, this very simplified receiver, and we were only looking at, let's say, voltage noise. So again, and this is very much, as I said, review from 240. If I have that comparator and from whatever reason its offset or its threshold is not exactly at 0, but it's actually skewed a little bit, right? Then if I wanted to figure out how many errors I'm making, then I basically just have to look at something that's related to essentially the ratio between sort of that input signal that I'm sending minus the offset divided by the standard deviation of the noise. Okay, and the reason that happens is just assuming, of course, the noise is a Gaussian signal, then basically I'm just sort of integrating the tails of the distribution to see how often is that noise actually larger than your signal. Okay? So kind of the key message here is just that, if you're talking about bit error rate, what you basically always end up with is you just need to know how many sort of sigma of noise is your signal, relatively speaking, right? Because the more sort of sigma of noise your signal is, then the less likely it is you actually make a mistake. Okay, so just some good numbers to remember are, if you want a bit error rate of about 10 to the minus 12, you need about 7 sigma of noise. If you want about 10 to the minus 20, you need about 9.25 sigma of noise, and so on and so forth. I trust you guys can actually do this inverse error function. It's not that difficult. Just plug it into MATLAB once, and you'll get an idea of sort of the shape of this curve here. Okay. Now, by the way, you'll notice that I quoted here only things like 10 to the minus 12 or 10 to the minus 20 types of bit error rates. So that turns out to be kind of a typical range for where high-speed links operate. Okay, so why is that? Why is it that people typically operate in this kind of 10 to the minus 12, 10 to the minus 20 bit error rate range? Anybody have an idea?
There's no channel estimation and correction usually.
Actually, no. There's plenty of channel estimation and correction. We'll talk actually a lot more about that, but there's another reason. You could have meant maybe slightly different, or maybe you meant slightly different than what you actually said, but I'll maybe see if we can get the right terminology.
Is that related to the data rate?
Okay, there is some relationship to the data rate. Anything else? Not you, just since I know you'll know the answer. Anybody else? Milos, you should know the answer. Okay, well, so you said something about coding. So yeah, there has something to do with coding there. But so why do you do coding in the first place?
To eliminate the errors.
Right, but so can you really actually make the errors go to 0 over all time forever, or is it more just basically you want to make sure that, again, you've hit some certain bit error rate at the end of the day? Yeah. Okay, you want to hit some certain bit error rate at the end of the day. What drives you wanting to hit that particular bit error rate? Like, how do you decide that it should be 10 to the minus 12 versus 10 to the minus 50 versus 10 to the minus 3? Like, how do you decide that?
How often you can tolerate errors?
There we go. It's all about how often you can tolerate errors, right? So it turns out, even if you look at, let's say, these telecommunications types of things, you don't really want to tolerate errors very often. Okay, now you can't make it 0, but you don't want to tolerate them very often. Okay? Because it turns out, okay, maybe even if you did get an error, maybe if you have a way of detecting that you got an error, you can retransmit or something like that, but that tends to be expensive. Okay, so particularly in a lot of the links applications, you can imagine if I've got terabit, 10 terabits, 100 terabits per second of data flying around all over the place, really expensive for me to just stop everything and say, oh, no, sorry, I got the wrong bit, please send that one again, right? So you tend to choose these kinds of numbers because you really don't want to be doing that very often. Now, just to sort of highlight that a little bit, if I have a 10 gigabit per second link, on average, how often are you making an error if I have a bit error rate of 10 to the minus 12?
Once per 100 bits?
Seconds.
No, well, 100 bits would be really bad. That'd be 10 to the minus 2. It's once per 100 seconds. You got at least the right calculation, I guess. It's once in 100 seconds, which, okay, that's actually not that long, right? Like, that's going to happen pretty often, okay? Now, you're right, you could put some coding on top of the thing. The reason you don't, we'll talk about later. It just turns out to be expensive in these particular applications. But as an example, if you compared this for, let's say, against wireless, where your typical data rates are much, much lower, let's say maybe we set up to about 400 megabits per second for something like Wi-Fi. Well, okay, that's pretty fast, but still quite a bit slower than something like 10 gig, right? And in fact, in wireless, they do use a lot of coding and things like that, which is why you'll see in those types of scenarios, they're usually operating in like 10 to the minus 3, 10 to the minus 4 types of error rates. Links, almost always designed in this kind of 10 to the minus 12 to 10 to the minus 20 range, okay? We'll actually talk about this some more later, but in kind of old-time computer systems, the time they wanted between sort of bit failures was nearly infinite. So this 10 to the minus 20 number here was actually typically what people would shoot for in those types of systems. Yeah?
How would you measure that?
How do you measure 10 to the minus 20? You don't. So what you do, of course, is you measure something that's, you sort of intentionally mess up the receiver, and then see if it's kind of tracking the curve that you expected. Now, actually, I'll be slightly mean, but I think this is true. In computer systems, what they basically did is they shot for this 10 to the minus 20. They turned the thing on. They ran it for an hour. If they didn't see any problems, they said, OK, we're good, right? Because, by the way, in a computer, it's not just one link that you've got there. You've got a lot of links, right? So if I've got 1,000-something links, even this 10 to the minus 20 number starts dropping pretty quickly. Okay, but you're absolutely right. Measuring 10 to the minus 20, even with a 10 gigabit per second link, is a lot of seconds, right? So that takes a while. Good question. Okay, cool. So now that we've sort of done the sort of the quick review of, okay, I've got noise, I've got interference, I've got distortion, they can all cause me problems because, again, I need to get these really low bit error rates. What I really want to mostly focus on for the rest of the day is kind of come back to that, basic link picture again, but actually talk about the part that has absolutely no electronics in it. Okay? So I want to talk about that quote-unquote wire. Because as we started talking about a little bit last time, if you actually look at what this wire really is, just as an example for, let's say, on a backplane, what you'd actually see is it's a fairly complex system. Okay? So you typically have some chip that's on the line card that's grabbing the actual data from the optical transceiver. Right? It's going to go through some trace on that line card, go through a connector. And by the way, this picture here is obviously my cartoon, but is not that far from reality. Okay? Goes through this connector, then goes through the backplane trace, and of course has to have a via there to do that. Goes back up through a connector, back into the line card. And then to actually finally, of course, get into the chip, you have to go through some package, you have to go through some solder bumps, You may even have some bond wires or flip chip bonds that you're doing, right? So there's actually quite a bit of sort of, all passive, metals and dielectrics and stuff, but there's a lot of things going on there. Okay, and as we'll see in 1 second, what's going on inside of this channel a lot of times is what's really driving our electronics design, okay, and why we have to do things the way we do. Okay, so the first thing that, again, should hopefully be a reminder for most of you is that, these are all, of course, just quote-unquote wires, meaning pieces of metal connected to each other, but that doesn't mean that they're actually all that easy to deal with. Okay, so certainly in integrated circuits, you almost always used, of course, lumped models for wires, right? Meaning most of the time in 90x% of the wires you've got, if you do anything, you sort of figure, well, okay, that wire has some capacitance in it, so I'll just model that, right? Well, and then, okay, sometimes the wire's long enough that you actually care about the resistance, so you'll go ahead and you model that. And then occasionally for crazy wireless people, they care about inductance or something, they'll actually even model that too. Okay, but usually sort of these, let's say, lumped models are a pretty reasonable thing to do. Well, of course, the trick is that making things so-called lumped only works because the dimensions you're dealing with are much, much smaller than kind of the wavelengths of interest, right? So just to sort of, maybe clarify what I mean by that and actually maybe give you some more examples, let's look at some example wavelengths and actually size numbers for the links that we're going to be talking about, okay? Just to sort of give you an idea of where things stand relative to each other. So what I'm going to do now is just sort of talk about kind of 3 typical types of links that you might see out there, and then just sort of look at what are the typical lengths and data rates you'd be working on. So the first one, which is in some senses the easiest other than maybe just on-chip signaling, is just basically 2 chips on the same PCB, and typically within pretty close proximity to each other, okay? So those types of links are basically, they're relatively short, meaning physically things are pretty close together. And they're also relatively well controlled, because if I'm all just on one PCB, there's only, let's say, one PCB designer that's kind of doing everything and connecting it all together, and they have probably a pretty good idea of what's going on, okay? So in those kinds of links, turns out it's actually usually the packaging of the chips that limits your throughput. Okay, that's usually where you pick up kind of most of the errors, and we'll talk some more about that a little bit later on. But just to kind of give you an idea, the typical distances you're talking about there are sort of 3 to 6 inches, maybe even 9 inches, or maybe at most like 10 or something like that. If you talked about the motherboard PCB for your laptop, but not too much larger than that, okay? And for just sort of typical data rates there, you're looking at anywhere from maybe about 1 gigabit per second up to maybe about 12 gigabits per second or so for kind of standards that are out there in the world today, okay? So what's, as we said before, this is all about how big is our thing physically compared to the wavelengths we care about. Well, so what are the wavelengths we care about for this context? What sort of sets that? What is wavelength related to?
Frequency.
Okay, speed of light and frequency, right? Okay, so what frequencies matter, roughly speaking, if I'm doing something from about 1 to 12 gigabits per second?
6 gigahertz.
Yeah, okay, so you said 6 gigahertz, that's sort of the up end. That's just because at least if I'm doing a binary signal, then I kind of have 1 bit that's high, then 1 bit that's low. If each one of those was 1 over 12 gigahertz, then of course that period there is 6 gigahertz. Okay, well, so who actually remembers what would be the wavelength, at least in free space, for a 6 gigahertz signal?
5 centimeters.
5 centimeters.
5 centimeters. Okay, yeah, that's right. So, by the way, I'm going to freely flip between centimeters and inches here, only because, from whatever reason, some people in some applications like to talk about inches. So, in particular, in these chip-to-chip things, everyone talks about how many inches the channel is. And from whatever reason, in other applications that we'll talk about in a second, they talk about meters. Okay, so does anybody happen to remember, how many inches that is?
2 inches.
Yeah, it's 2 inches. Okay, so it's about 2 inches at the high end. And then if I was going to go down and, go back to the good old days and go to like a gigabit per second or something like that, how long is that going to be?
12 inches.
Yeah, it's 12, right? Actually, no, sorry, it's 24, excuse me. Because just factor of 12, right? Okay, now that's free space. So what happens when we actually, send that thing on a real wire surrounded by a dielectric, and in particular, usually in PCBs, that dielectric is FR4.
Square root of epsilon r.
Yeah, okay. So basically the speed goes down by square root of epsilon naught, right? Which means that the wavelength gets shorter. Okay, so now if anybody happen to know what the dielectric of FR4 is? Yeah, it's about 4. It's 4.357, somewhere in that ballpark. Okay, but I just call that 4 because I'm lazy. Okay, so there's just basically a factor of 2. So now we're at, an inch to maybe up to about 12 inches. Okay? So, what does this say? Like, can I treat things as being lumped or not? What do you guys think? Okay, so I see, well, maybe we'll take a vote. So who thinks this is all great? We're lumped. It's easy. Not lumped? Okay, of course. Now, why not?
Well, the dimensions are not much less than lambda.
Okay, well, so what do you usually mean by much less?
Order of magnitude.
Yeah, okay. So obviously the engineering rule of thumb, so to speak, is that order of magnitude number. Okay, so yeah. By the way, if I went up to like that gigabit or so, I went up to this like 12 inches. Okay, obviously that's not much less. That's still, pretty comparable. It's only a factor of 2, but turns out even if you're going at these lower data rates, remember actually a sinusoid is kind of, let's say, a little bit slow, right? Because you're only at the peak value for a pretty short time. If I actually want a nice square bit, then the edges themselves are actually going to have much higher frequency content in them. And again, this is something we'll talk about next time. But actually, so there's a pretty sort of, let's say, clever game you have to play between making sure that your edges are sort of fast enough, but not making them too fast, because if you make them too fast, then everything looks distributed, right? And everything may actually look bad. Because it turns out, as we'll see in 1 second, it's hard to actually make distributed things really, really clean from an environmental standpoint. Okay? So that's the first sort of type of link. Okay, so the next type of link, which is again fairly common, is just cables basically connecting things together on different PCBs. So this could range from anything like USB, right, which you guys I'm sure all know and familiar with, to even things like Ethernet. Okay, because Ethernet is actually a few different types of cables. You could have that between, let's say, different racks in a backplane, or even obviously between your computer and some router somewhere, and so on and so forth. Okay, so it turns out that in those contexts, the cable itself, from a, let's say, signal integrity standpoint, is typically pretty clean, as long as it's a reasonable coax cable. The only bad news is that it's a little bit lossy, or in fact, maybe even a lot lossy. We'll talk more about why that is in 1 second. But actually, a lot of times, the biggest issue you end up facing in those systems is just connecting to that darn cable. Okay, because as we'll see in a second, connectors are almost always where things get nasty. Because basically, from a very high-level standpoint, if you want to make the connector small and sort of have actually a lot of things going through it, it's pretty tough to keep a good signal integrity environment there. Okay? So typical distances you're talking about in these so-called cable links is anywhere from, let's say, maybe about half a meter or so. Again, for that short USB cable you have for your iPhone or whatever it is, up to maybe about tens of meters if you're really talking about these Ethernet types of applications. Okay? And again, data rates range anywhere from about 1 to 10 gigabits per second. Turns out in Ethernet, if you do 10 gigabits per second, you're not doing signaling the same way that I'm talking about here, because you actually do multi-level signaling, because those channels are really bad. But data rate-wise, at least that's the range is pretty constant here. Okay, so just to do our little exercise, so what would be sort of our wavelengths of interest here? And I'll just convert it to meters this time, because again, from whatever reason, cable people like meters, and board people like inches. So we'll roughly kind of, what wavelengths are we talking about here?
5 to 50 centimeters.
Yeah, basically. So somewhere like, and I guess I did the calculation, it was about 0.6 meters up to about 6 meters here.
Oh.
Right? And then, obviously if you're on the board, then it's about 0.3 meters to about 3 meters or so. Okay, so again, clearly pretty distributed. Okay, so I guess you could maybe argue again, down in that gigabit per second, if only going half a meter, then maybe that's, not such a big deal, but, that's kind of the ballpark that we're talking about here. Okay? So, last type of link that I'll just sort of briefly mention is actually basically these, what's probably we'll spend a lot of time in the class, because it turns out it's one of the most challenging ones, is these so-called high-speed board-to-board connectors. So, or board-to-board, let's say, links. So that's the situation where, for example, you have these backplanes, right? And not only do you have this like big PCB as the backplane, you actually have all these other boards connecting into that thing, okay? So not only do you have to sort of get through one of the boards, you also have to go through some connector, go through some other board, back through the connector, and so on and so forth, okay? So these other boards sometimes are referred to as daughter cards. So like the backplane is kind of like, let's say, the master or the big board, and the daughter card is the thing that kind of plugs into it, okay? There's obviously different types of those, and we'll see that more in 1 second. And again, they obviously plug in through these connectors, okay? So again, in backplanes, don't ask me why people like inches, so we'll go back to inches. So typical backplanes are anywhere from about, typical channels are anywhere from about 8 inches up to about 40 inches or so. And that's just sort of, to go back maybe to our picture over here, that's just kind of the variation between, there's obviously more of these line cards on here. That's just kind of the variation between getting out of this thing, going through, and then coming to the closest line card, versus coming out of that thing and then going over to the farthest line card or farthest switch card, as the case may be. Okay? And so again here, signaling rates-wise, we're talking, so ballpark 5 to 20 gigabits per second or so. Okay, so again, similar range, maybe a little bit higher in this particular example. All right, so just, to get everybody, or make sure everyone's awake, what's the wavelength now? In free space. What's kind of the range there?
10 to 140.
Say that again?
4 to 20.
4 to 20 what? Oh, in inches.
10 to
10 to
40.
Yeah, well, 10 seems actually a little bit high because we said, well, we can go back here. So we said 10 gigabits per second. Oh, sorry, yeah.
So it should be.
Sorry, 1 to 4.
Yeah, so at 10, or excuse me, at 12 it's 2 inches. So at 5 it's, 4 point whatever, about 5 inches or so, right? So let's just call that 5 inches. And then on the other end, oh, actually that's the long end. And then it just gets smaller than that. I'm lazy, I don't feel like doing it, right? Yeah, but bottom line, again, still definitely distributed, right? Certainly the case that wavelengths are all pretty small in comparison to the distances we're talking about. So bottom line here, of course, is really that we get to deal with our good old friends, transmission lines, okay? So I just want to do a really sort of quick review here. I'll spend maybe literally like 2 minutes on this because I'm pretty sure most of you guys know it already, but just to make sure we're all sort of on the same page. When we talk about transmission lines, there's really sort of, let's say, 2 main characteristics that you care about, okay? So the first is really just, what's the delay of the line? Okay, and what I mean by the delay really often translates into just, what's the physical length of the line, right? Because remember, the whole point with transmission lines is that speed of light actually matters. You can't get from point A to point B instantaneously. That's why you actually have to deal with this transmission line kind of stuff, okay? So this is, of course, again, as I said, related to the length. And as we said before, it's also related to the dielectric constant. Okay, so if you have a material with very high dielectric constant, that slows the wave down. It takes you longer to cover a certain physical distance, okay? The other thing, of course, that's important is the characteristic impedance. Okay, so hopefully you guys all sort of remember this from somewhere, and I'll just draw the picture in 1 second. That's just square root of L over C. Okay, and by L and C, I just mean, nice way to model a transmission line is just to say it's essentially just sort of this distributed, or rather I should say, sections of L's and C's kind of cascaded like this, right? Because that's just sort of modeling essentially energy being stored in the magnetic field, then transferred to the electric field, and back and forth, right? So characteristic impedance is just sort of the ratio of those 2 quantities, okay? And, also just to be, let's say, 100% clear, usually the sort of symbol for that is something that looks like this. To be very precise, usually, or sometimes people will actually also show the ground shield on there, because this is kind of reminiscent of a coax cable. So sometimes people actually draw that line there. That's what people mean by that, okay? Now, there's, of course, sort of, these are kind of, let's say, the basic characteristics. So as we said, there's some characteristic impedance, Z naught. There's some delay for that line. But as we'll see, and as I'm sure you guys have seen before, there's also other, let's say, fun things that happen when you start dealing with transmission lines. The first fun thing is these so-called reflections. Okay, and we'll see that more in 1 second. The second fun thing is that even though I drew this, of course, as being just this LC kind of thing, well, any real wire has resistance in it. So unfortunately, every one of those inductors actually has a resistor in series with it. And actually, not only that, as we'll see in 1 second, unfortunately, any like capacitor also actually ends up having some effective parallel conductance there. Okay? And again, we'll see sort of physically where that comes from in 1 second. And oh, by the way, those conductances and resistances actually depend on frequency. So they make life a little bit more fun, so to speak. Okay? So let's just sort of do a quick review of, let's just talk about reflections. Okay? So the whole trick here is that because everything's limited by the speed of light, what this basically says is that, you know, if I have some transmitter over here, it's talking to some receiver over there, you can't instantaneously know what the characteristics of the receiver are. Okay? So what that means is that if I go and I send some information from the transmitter, at first all it can see is the characteristics of whatever transmission line it's driving. Okay? But if by the time you get to the receiver, you actually hit some other kind of characteristic, for example, you had maybe just another transmission line with a different characteristic impedance, well, somehow you have to sort of balance things out, right? You have to send the information back to the transmitter to say, oh no, by the way, actually you're not talking to a 50 ohm line, you're talking to 100 ohms, you know, load resistance or something like that, right? That kind of says there's always going to be reflections whenever you hit these so-called discontinuities, okay? So what this bit, you know, the way you sort of always figure this out, turns out I never really remember these equations. I always just go back and derive them when I really need them. And the way you do that is you always just remember anytime you have a junction like this, then energy has to be conserved. And at this one particular point, of course, the voltages have to be equal. Okay, so if I basically look at what was the voltage that I transmitted, what's the voltage that's reflected, and what's the voltage that basically goes through, then essentially at that point, the transmitted voltage has to be equal to the reflected voltage plus the voltage sent through. Okay? And if you use that and energy conservation, you'll get these nice sort of, you know, what's called the telegrapher's equations telling you what happens with those reflections. Okay? Now, you may think that I'm just sort of telling you about this because, you know, it's a nice academic curiosity. Well, turns out this is actually very, very relevant to all of the stuff that we're going to be dealing with. Okay? So in fact, if you look at any of those, let's say, backplanes or even actually in the chip-to-chip kinds of applications, you'll find plenty of places for impedance mismatch. Okay, so just as an example, if I looked at, you know, on one of those backplanes, if I looked on the daughter card, I may start out with this kind of 50 ohm impedance, but then I have to go through a via to get to a different layer. Well, darn it, impedance of that via is not quite 50 ohms. Okay? Then maybe I go through some connector somewhere, and okay, that's kind of roughly 50 ohms, but is, you know, wiggling around a little bit. Then I go through another via with another, let's say, bad or different impedance. And I come back to the backplane, which is, okay, maybe that's kind of roughly 50 ohms. And actually, eventually, I'll get to the transistors, which also usually are not 50 ohms, and so on and so forth. Okay? So I guess if I was really mean, and you'll see an example of this in 1 second, you know, classic really mean homework problem is to give you like a cascade of 5 different transmission lines with all different Z-naughts and all kinds of weird stuff happening, and then have you track all of the different reflections that happen in this nasty thing. Okay? The other sort of big effect that we have to worry about in terms of transmission lines is, of course, just that they're lossy. Meaning that, you know, if you send stuff, you send a voltage at one end of the line, you may not actually get exactly that same voltage on the other side. Okay? So the first sort of loss mechanism is so-called skin effect. So skin effect is just sort of, let's say a fallout of the fact that current always wants to flow through the lowest impedance path. Well, at high frequencies, that means that you want to sort of have as little inductance as you can, which means you want the return path to be sort of as small of an area as you can. So if you sort of think about that in the context of a wire just over, let's say, some ground plane or something like that, that means that at high frequencies, all of the current gets pushed out to the edges of the wire, right? Because that means that sort of the loop the current has to do is as small as possible, right? Because if I actually had stuff in the middle, I'd have to traverse through the wire to actually, you know, and that would cause me some inductance. Whereas if I'm always flowing on the edge, then that just reduces the inductance that I have, okay? So that's, you know, you'd kind of think that maybe that's good news, but turns out that's actually sort of bad news because it means your loss is going to be higher, right? Because sort of the effective thickness of the conductor is not really set by physically how thick the thing is, but actually by how high of a frequency you're actually signaling at, okay? So this is characterized by what's called the skin depth. That just means sort of like how deep away from the surface does the current really flow, kind of on average. Okay, it's proportional to something like the square root of the frequency. And so then basically what you'll do is you'll sort of model it as if you're only flowing through that delta thick sort of ring around the edge. And then basically what you'll see in 1 second is that, as you can imagine, actually you can see on the plot here, once this really starts coming into effect, then your resistance just starts going up very, very quickly, which means your loss also actually goes up very quickly. So in particular, what this basically says is that the loss is kind of related to the exponential of the square root of the frequency. Okay, and we'll see that again in 1 more second. Now, I guess the only good news is that, your conductor always has a finite thickness. So at lower frequencies, where kind of the skin depth would be larger than the conductor size anyways, it kind of doesn't really have an effect, right? So this really only kicks in at the frequency at which your skin depth becomes comparable to the dimension of the conductor you're using, okay? So this is just sort of, let's say, some nice pictures that people got from doing some field solver simulations, just to really prove that, yes, if you look at different frequencies, the current indeed does actually flow closer to the edges. So just to make sure it's sort of clear, because this confused me when I first looked at it too, this thing over here is the bottom of that wire, which is just a wire over a ground plane. Okay? This is the top of that wire. So I'm sort of just taking like one section and looking at what happens as I move vertically in that wire, meaning that I move away from sort of the bottom of the conductor. Okay? So what you can kind of see here is that, of course, at 100 megahertz, okay, there's certainly some variation there, but there's still pretty reasonable distribution of current, because at that frequency, the sort of the skin depth is large compared to the dimensions of the particular conductor I used here. Okay? Then as I go up to 500 megahertz, you sort of see these spikes on the edge, and in particular, you see there's a lot more current on one side than on the other. Well, that's because that's closer to the bottom, right? Of course, if I go all the way up to a gigahertz here, now really most of the current is kind of flowing on the bottom because it really wants that low inductance return path back through the ground plane. Okay? Make sense to everybody? Or? Okay. So the other, of course, let's say piece of fun that you get is not only do you have the skin effect, but actually have what's called dielectric loss. So where this comes from is kind of an interesting one. So basically, you'd sort of think, well, I just have a capacitor, right? So why does a capacitor have any loss in it? Well, turns out dielectrics, they all have basically molecules in there that are getting polarized, okay? Well, at really high frequencies, those molecules basically can't follow the signal you're applying as fast as you're trying to apply that signal. So what that basically means is that you're sort of dragging the signal, the molecules through an electric field, okay? Well, if I'm dragging those molecules through an electric field, that basically implies that I've got loss in my signal, okay? So in other words, the insulator is actually absorbing some of the energy of your signal and just converting it into heat, okay? So this particular effect is approximately linear with frequency. It's usually modeled with what's called the tan delta, which is like the loss tangent. Don't ask me why they decided to come up with that. That's just usually how they sort of talk about it. The long story short is that it basically tells you that, again, your loss sort of increases exponentially with the distance that you're traveling. Okay, because basically you pick up more and more of this dielectric material that you have to basically heat up as your signal is propagating. Okay? So this little table here just kind of gives you some example numbers for what that loss or that loss tangent actually ends up being for a few practical materials. You can see that, of course, FR4 ends up being one of the highest one of them. And, maybe just, to see how many of you guys are tuned into Murphy's Law, which one is, of course, out of the table here, which one of these is, of course, the most common dielectric for you to be using? FR4, right? Because it's cheap, it's ubiquitous, but, sorry, has the highest loss. Okay, so usually, again, this is indeed something you just end up having to deal with. Okay? So if you sort of look at this, in terms of loss versus frequency, then, as we already said, FR4 is indeed cheapest. So you can look at what would happen with FR4 versus, for example, that's the red curve over here, versus what would happen with this other material, which is this particular one is called Rogers 4360, just some other dielectric composite. I have no idea actually what's inside of there, but basically they're trying to arrange it to have lower loss. And as you can see, of course, if I went out to really high frequencies, pretty big difference between, this 40 dB of attenuation versus like 10, right? So would be really nice if you could use that. And by the way, Rogers is the most expensive one, but it's pretty uncommon because, again, it's pretty costly to actually put that into place. Okay, so it's really only very high-end systems that would sort of get to use Rogers. For those of you guys who sort of like this kind of stuff, it turns out one of the other reasons they tend not to use this that often is because even though the dielectric itself may have pretty nice qualities, if you actually end up with a conductor that's a little bit rough on the surface, you can actually end up with very similar phenomenon. Okay, so to actually really make this worthwhile, you not only have to invest in this new dielectric material, you actually also have to make the conductors themselves really, really smooth and really, really pristine. And again, that just turns out to be difficult to do and therefore costs you a lot of money. Okay?
We're a lot higher on the bottom, obviously, because they're attracted to the...
You're talking about over here?
Yeah.
Uh-huh.
So they're attracted to the electrons.
Exactly.
or
So all
holes
that's
on the
really
bottom.
happening here is if we just sort of draw, let's say, a little zoom in of that particular picture. Right, so if I've got my conductor over a ground plane, then really all you're trying to do is sort of minimize the loop that's kind of, going into the page and then flowing back out through the ground plane. Right? Because if I've got current flowing out, let's say over there or in the middle or something, it has to flow back through a longer loop to get through that.
So do you just need to smooth the bottom of the conductors mainly, or is it...
Oh, well, so you can see there are, let's say, some edge effects and things like that if you don't include, you'll get not exactly correct. But basically what this really says is that, if you go back to kind of this model, it's really just kind of confirming that it's a pretty reasonable assumption that things will only be flowing kind of on the edges of that conductor. Now, it is indeed true that if you have something that's sort of asymmetric, meaning there's a ground plane on the bottom and not on the top, you will indeed get slightly different loss characteristics than something that has a more symmetric type of structure. Other questions on this? Or?
Is that mainly because the current is flowing different direction, so the mutual conductance will be minus term. Then if you get closer, minus term is larger, right?
So, which effect are you trying to explain?
I'm saying why it's getting closer to the ground plane.
I think it's getting closer to the bottom. I mean, there's probably a much better, let's say, electromagnetics way of explaining it, but I think intuitively the easiest explanation that I know of is just that basically, you're trying to make that net impedance as small as you can. And at high frequencies, inductance matters a lot, right? So that really means you try and get pushed as close together in the surface as you can just to minimize the area of that loop.
But my question is, if they are flowing in the same direction, then you should want to push them as far as possible. Not as close as
I see. I'm
right.
sorry. I misunderstood your question. That's
I
right.
was thinking,
Yes.
yeah,
Yes,
the
that's
same
right.
thing, yeah.
That's right. That's right. Other questions? Okay. So we talked a bit about this dielectric loss. As I said, it's exponential with frequency. Of course, any real thing has both dielectric loss and skin loss, or skin effect, which here I've just labeled as being conductor loss. So just as a reminder, that skin loss is proportional to the square root of frequency. Again, remember, but when I say square root of frequency, that means the resistance is increasing like that. So actually the loss is increasing exponentially, meaning it's square root of f in dB. Similarly, the dielectric loss, also proportional to frequency in dB. So as you can imagine, beyond some frequency, essentially it's dielectric loss that really is the big dominant factor. Because if one is sort of only changing with square root and the other one's changing with f, there'll always eventually be some crossover point. Okay, and that's, if you sort of look at what this plot is showing you here, it's just saying if I look at the total loss, at low frequencies I'm actually dominated by that conductor loss, which just means kind of the finite resistance. Then over this range right here, I'm kind of dominated by still the conductor loss. But then once that dielectric loss really kicks in, that's kind of what dominates my curve. Okay? And this is, again, very, very typical sort of behavior because simply, if one's square root and the other one's f, there's always going to have to be a crossover. Okay? Okay, so if we kind of take all these things and put them together, at the end of the day, what people usually like to look at is, okay, fine. What is it that really happens to my signal? So if I look at what is it that I'm sending and what is it that I'm receiving, just tell me at the end of the day what's kind of the relationship between them. So partially because a lot of the people who sort of work in really fixing these channels have a microwave background, they typically like to talk about it in terms of scattering parameters, or these S parameters. So a lot of times you'll hear that people talk about the so-called S21 of the channel. So just for those of you guys who haven't heard of that before, S21 just literally means what's the ratio of the received signal to the transmitted signal. Okay, that's really all you have to think about it as. So, and again, as you can see, you know, there's lots of different types of channels that you may have. You can, of course, take different components and try and cascade their S21s, as long as you're, of course, careful about the matching and things like that. Okay? But if you do that, then indeed you can sort of get an idea of overall what does your channel actually look like from a signal integrity standpoint. Okay? So this was mostly to sort of just give you a high-level overview of just, you know, what are the things that physically we're going to care about in terms of just, you know, transmission lines and reflections and, let's say, you know, where the loss mechanisms come from. But what I want to do now is actually start looking at examples of what do real backplanes actually look like, and what are some of the issues that you're going to come across because of all the effects that we just talked about. Okay? So this isn't actually a real backplane. This is actually more like a backplane characterization kind of thing. But idea is actually very similar. Okay? So again, as we've sort of seen a couple times now, you've got this big, long sort of main backplane card that's holding all of the line cards and all of the switch cards. So these vertical riser things, that's where the sort of line cards or switch cards would be sitting. And then you can see there's these connectors here that actually have to be very, very dense, right? Because I want to get a lot of signals off of that line card or off of the switch card, as the case may be, and send them out into the rest of the system. Okay? So in fact, if you actually take a look at the inside of these connectors, turns out they're actually pretty complicated little things. And as we'll see in one more second, a lot of the issues we're going to end up facing are because of these connectors here. Okay? Because this is oftentimes where things sort of have to be the densest, and therefore where you end up with the most problems in terms of actually trying to maintain a clean environment. Okay? So, of course, if we look at, you know, on that backplane, what do these signals actually usually look like? Typically what you're going to do is some sort of differential signaling. Okay, now, I guess since all of you, I said from the get-go, are supposed to have taken 240, I don't have to spend a lot of time on talking about why differential is good, right? It allows you to reject a lot of the common mode noise, and trust me, in a big backplane with thousands of links and, you know, memories and processors and stuff, there's all kinds of common mode noise all over the place. Okay, so that's good news. But really, I guess sort of the point that I want to highlight here is that, you know, just remember, the only thing that makes things really quote-unquote differential is that you have strong mutual coupling between the two lines that you actually want to be differential and less coupling between them and the rest of the world. Okay? So that means that in essence, what you really have to do is sort of control the spacing of the differential signals compared to anything else out there that you're interested in. Okay? So actually, while I'm on that particular topic, if we really think about coupling, and we've talked about differential already, well, as we've said before, bad news is that even though I have these nice wires all over the place, well, they actually can couple to each other, right? So even if I do a really good job and I build nice, you know, differential transmission lines, well, if I've got other transmission lines around, turns out they will couple into the things that you do actually care about, okay? So just to give you a little bit of terminology here, there's basically two different types of crosstalk, which really, again, crosstalk obviously just comes from this coupling behavior. The first is what's called near-end crosstalk, okay? So the idea with near-end crosstalk is that, you know, let's say I send some signal somewhere, and then all of a sudden I hit an impedance discontinuity somewhere. So in particular, I could have like my transmitter chip and I go out through a bond wire. That bond wire doesn't really have a perfect impedance behavior. Then it hits the transmission line. I get a reflection, okay? Well, for near-end crosstalk, that reflection basically will travel it'll couple over into this other line as well and travel back towards where you sent the signal, okay? So in this particular case, you can see I've got the transmitter sort of jumping over and heading back towards this other receiver, okay? That's usually what's called near-end crosstalk. You also have what's called far-end crosstalk, which this one is usually, let's say, a little bit more, let's say, obvious in the sense that this is the one where I basically send some signal in this particular direction. But again, because I see some impedance discontinuity or I have some coupling between the lines, I will basically also couple onto the other line. And then it'll travel basically in the same direction as the original signal was. Okay? So as you can kind of hopefully tell from this picture, the near-end crosstalk in particular can be really, really nasty, right? Because what you basically have is you've got your transmitter, which has this nice, healthy signal that it's all ready to go and send. And if that transmitter is basically close to the receiver, and it has some coupling into it, then now you're going to take that nice big transmit signal and slam it right onto your small receive signal that you're trying to tell what the hell that is inside of all this noise, right? So for most of the sort of signal integrity things, people pay a lot of attention to this near-end crosstalk. That's not to say that far end, and by the way, people call these next and fext, just because I guess saying crosstalk all the time is a little bit annoying. So, though, in particular, you really have to pay attention to that next, okay? Now, the good news is that if you do a good job with the design, you really can control this reasonably well. But kind of typical numbers that you'll run into is somewhere in the range of about 3 to 6% for that near-end crosstalk, and something like about 1 to 3% for the far-end crosstalk, okay? Yeah?
So for newer chips that are running at, say, 20 gigabits, are we talking about flip chip designs or?
It's a great question. So most of them probably are in flip chip designs, but I wouldn't say that that's necessarily ubiquitous, because a lot of times that's really driven by, if I've got, I don't know, let's say some low-cost FPGA that I want to sell you, and I tell you, oh no, but sorry, by the way, you have to buy an expensive flip chip package, not going to cut it, right? And I may still actually want that 20 gigabit per second link. So as we were actually mentioning before, sometimes, even though there's all this other backplane and cables and etc., sometimes it's just your darn package or your bond wire that's actually causing a lot of the signal integrity issues. Yeah?
So why did you say next can be pretty well controlled through design?
Okay, great question. I'll tell you why. So I'm going to show you what not to do, and then I'll show you what I think is a little bit better to do. And by the way, the answer is fairly obvious, but you'll see in 1 second. Okay? So this is actually an example of, let's say, what could go wrong with near-end crosstalk. Okay? So I'm sort of showing you two different scenarios here, but they sort of both translate into the same thing. So here I'm just showing an example of how I might arrange the backplane. Okay? So I might arrange the backplane so that I've got a transmitter, then a receiver, then a transmitter, then a receiver, and so on and so forth. Right? So I'm just sort of alternating between them. Okay? Similarly, if I looked at, let's say, the connector, and this is kind of looking at the top view going down, okay? I could also arrange it so that I have a transmitter, then a receiver, a transmitter, then a receiver, and so on and so forth. Okay? By the way, these little gold things over here, these are essentially ground lines. Okay? So that's obviously to try and make life, let's say, a little bit better. Okay? So, and by the way, these are sometimes called ground blades in the context of connectors. Okay? So, nonetheless, if I do some arrangement like this, so in particular, if you think about this picture, you remember this is a vertical picture here. Okay? I may not actually, if this is kind of like, if I'm taking this thing and plugging it in to that, I may not actually have these ground lines going up vertically, right? I've only kind of got them in this transition region here. So that actually means that once I sort of hit this point, A, I'm going to get some discontinuity, right? And then B, I'm going to get some coupling, okay? Because that discontinuity is going to sort of flow back through the receiver over here, okay? So if I look at it, just as an example, if this is, let's say, what I transmitted, and this would be the received signal that I would have gotten, this thing over here is like the near-end crosstalk that I would pick up from the transmitter. Okay, just due to this sort of discontinuity that I hit at that connector point. Okay? Well, it turns out I can do a very simple, change to my design that makes things a lot better. Okay? So just as an example, if instead I actually arranged all of my transmitters in one row like this, and all of my receivers in one row like this, and then actually kept the ground shield in between them on the PCB, well, now, okay, you're still going to get some near-end crosstalk. There's kind of no way around that. But now, at least if I have this sort of low impedance ground plane in between, most of the junk, so to speak, is absorbed by the ground plane. Okay? So this is an example of how you can do a better design to actually try and fix some of these crosstalk issues. And by the way, by design here, clearly this is not your chip, right? This is your connector, this is your package, this is your PCB, etc. Okay? Does that answer your question? Or?
Yeah. But then, is there something we can do on chips?
Okay, great question. So you were asking, is there something you can actually do on the chip? So the answer is, You want the flippant answer or you want the technical answer?
Well, either way.
Okay, so the flip answer is that it's painful. Okay? The technical answer is yes, indeed. If I knew what the crosstalk was, right, and I literally had, my transmitter and my receiver and another transmitter and another receiver, and I knew the data that I was going to be transmitting, and I knew that it was going to hit my receiver, indeed, you could do crosstalk cancellation or crosstalk correction or something of that nature. The practical issue you tend to run into is, if I'm going to build this, transceiver thing, I probably want to sell it to a bunch of different people in a bunch of different backplanes. So I might not necessarily know that this particular receiver is the thing hit by this particular transmitter, right? And in fact, if you think about one of these really big chips, and in fact these really big backplanes, and if you actually look at some of, let's say, the link budgeting that people will do, turns out you may actually have 5 or 10 different crosstalk sources from 5 or 10 completely different switch chips, right? Because in that backplane, all those signals are running next to each other. In the connectors, they may actually be next to each other. I may have some vias somewhere that are causing some of those reflections, right? So in principle, yes, from a, if I was an information theorist, I'd say, oh yeah, absolutely, I can do multi-user detection or whatever you want to come up with. But in practice, really hard to get, at 20 gigabits per second to know every single piece of data on every single chip so that I can really do that cancellation effectively. So there are actually some works that people have done, mostly in the really, let's say, the short chip-to-chip I/O kind of context, where you really can say, okay, I've got a bus of things. I know all the data on the bus, so I can kind of do something there. But I think in practice, I haven't seen any of those solutions actually deployed. It's a great question. Other questions? Okay, good. So, as I've mentioned a couple times now, it turns out the connectors are really what's kind of particularly tough, especially from the standpoint of this crosstalk. And as I mentioned, the reason for that is because you basically, in these connectors, have to do a lot of things all in one place. Okay, and if this is kind of just a picture or sort of an example of what one of these standard connectors kind of looks like. Really, the key driver here is all about just, if I'm doing a connector, I want the thing to be small, right? Because it's literally just getting me from one board to the other board. If I have to make my board 3 times as big just because I have a connector on it, bad news, right? Because I can fit a lot less stuff than I used to be able to. So what ends up happening is that to really build these connectors, it's pretty tough to get them to still be nice, clean differential traces, right? You can kind of see, just as an example, if I want to do one of these things where I have these, and I'll go back to the picture here, where I've got the board sort of sitting vertically like this, and then I plug the connector in that way into the daughter board, but I want it to go down into the backplane, right? I have to do this sort of weird transition thing, right? And so what you can see is usually the people who end up having to do that is they do these kind of weird bends and splits to sort of break back out into the PCB pitch, right? So you may have one pitch on the PCB, but in the connector you want it compact, so you'll sort of bring things in together, then fan it back out. Again, turns out really tough to actually make all these signals nice and balanced with each other, okay? So what you'll typically see is you'll pick up quite a bit of skew, for example, between pairs inside of this connector. That's kind of what this table here is saying. Basically saying if I looked at the delay from, for example, H to H prime, that's about 200 picoseconds, whereas from A to A prime, it's only about 99 picoseconds or something, right? So again, and you can imagine, okay, maybe I could have done something to try and compensate for that, but inside of this little connector where I'm really, really tight, I'd have to spend a lot of space to do it, right? So what you'll oftentimes actually even try and do is, especially if you're the backplane designer, is you'll intentionally try and compensate for this skew somewhere else, okay? Now, of course, you have to be careful because just like with circuits, right, different components vary in different ways, and so you have to be really careful about that. But sometimes you sort of don't have a choice, okay? And as I mentioned, this is also a pretty big source of impedance discontinuities because also hard to get the grounds properly routed. They always have these bends and turns in them. Actually, it's a lot of times they'll even have breaks in them. Again, big source of discontinuities, okay? So while we're on that topic, in this, oh, yeah.
Since you have different delays for differential paths, how much, well, these percentage numbers, is that accounting for like the reduction in common mode immunity, or?
Okay, so these are actually just measuring sort of, let's say, the differential. It's a coupling from one differential channel to another differential channel in that percentage. The other thing I was actually going to mention right now is turns out that, you really do have to be very, very careful about differential wires in terms of routing them and keeping them balanced. Because it turns out, as you've said, you could sort of think of it as, well, okay, if they're not balanced, they'll get really bad common mode immunity. Well, even just from the standpoint of the signal, if my plus and minus are misaligned, as you can kind of see in this picture here, my eye diagram gets completely messed up. Right? So if I just took, for example, here I have 0 UI or 0, like, UI, by the way, just means unit interval. That's like the bit time. If I have both my plus and my minus lined up perfectly with each other, nice clean eye like this. If I just take the plus and the minus and shift them by half a bit relative to each other, well, guess what? You're getting garbage for a large period of the time. It's basically, you've thrown away half of the time where you actually could have gotten a reasonable signal. Okay? And by the way, just to convince you that maybe half UI is not actually that hard to pick up if you weren't careful about it, if you just think about a 30-inch line, if I just had 1% skew on that 30-inch line, that's 50 picoseconds. Okay? So if I'm going at 10 gigabits per second, that's indeed half of my bit time. Okay? So that tells you that, obviously if people really are going at these 20 plus gigabit per second kinds of rates, they're doing a really good job of keeping the skew on these big, long PCBs really, really small. Okay? Because if it wasn't, then you'd have really, really bad time actually just getting through on anything on the other side. Obviously, your, as you said, your common mode rejection and everything else is also a lot worse, but I think actually this is one of the even bigger issues. Does that make sense? Or? Great. Okay, so the only thing I should mention here is that, as I said, the backplanes themselves, the good news is things can be pretty well controlled. I'll get to you in 1 second. But as I said, it's really the connectors where usually a lot of the issues pop up. So the only piece of good news is that even though those connectors are pretty nasty, they're at least small. So the sort of net amount of skew you can pick up usually is relatively small. Okay? Or if there is some skew there, you might be able to just sort of put a little piece of line on this long PCB somewhere, again, to compensate for it. Yeah, Shiva, question?
Yeah, so how do you compensate for it with all these process variations?
Okay, so the good and the bad news is there's a little bit less that can vary in PCBs than, for example, in a transistor, right? Because there's just not that many different things going on in the PCB. Okay, so it turns out kind of the biggest sources of variations on the PCB are just things like temperature, humidity, things like that. And they have an effect, but it's nowhere near as bad as the kinds of variations you'd expect on a chip. Okay? And in particular, as long as you have, let's say, similar thermal expansions and things like that, you can do it reasonably well. Now, you're absolutely right, that is indeed an issue, right? Because if I have one piece that I've compensated with something else and they're both varying in completely different ways, you're absolutely in trouble. Right? So that's certainly something that from a, let's say, a link budgeting standpoint, and in fact, even from a link modeling standpoint, people will actually go in, they'll take their VNAs, vector network analyzers, they'll plug them into these backplanes, they'll put that in a temperature control chamber, they'll actually change the humidity, they'll measure it on different times of day or phases of the moon or whatever, right? They'll really check how much variation do you actually see in that particular channel. Does that make sense? Or? It's a good question. Yeah?
How do they control, I know the PCB dielectric constant tends to be all over the place.
It is indeed all over the place. That's true. Now, remember, just like with, let's say, your IC layouts, if you're doing matching, you try and make things as close together as meaning as closely matched as you can, right? So that hopefully if there is some global variation in the parameter, at least it's affecting both of the lines in the same way. Now, that's not to say that that doesn't mean, that if I looked at the S21s of those different channels, they could indeed actually vary quite a bit over the manufacturing range, which, as we'll talk a lot more later, that means that, even if you knew exactly sort of which PCB you were going to be working on, there's still going to be some range of adaptability you'd need just to handle the variations in the PCB itself. It's a great question. Other questions? Okay. So this is just sort of another, let's say, fun view of those reflections. You'll actually be getting another view like this in your homework. This is just, again, to tell you, I said those connectors are really annoying. Well, okay, if I've got, let's say, my daughter card thing, going through the connector, going through the backplane, going through another connector and back, well, if those connectors are sources of reflections, well, I can have all kinds of these fun bounce diagram things now, right? Because I go through, I hit that connector, I reflect back once. I have perhaps, another one that on this direction, which will reflect back and cause crosstalk, and so on and so forth. Okay, so if I sort of look at this in the time domain, again, for those of you guys who are sort of familiar with wireless, this is a lot like so-called multipath effects, right? Because I kind of have physically different lengths of time or different lengths of actual stuff that I've traveled to finally make it back onto that receive point. So if you sort of looked at, an example, just I put in 1 bit at a particular time, and then I looked at all these little things that are happening afterwards, these kind of groups of reflections, you could figure out roughly where they happened, just based on how long it took them to show up over at your receiver, okay? And so indeed, this is actually, when you look at these so-called S21s, or really these channel responses, a lot of times you just end up looking at, oh, well, where the heck is this, thing coming from? And what caused that? And, is there something I can tweak in the backplane that will maybe actually make it a little bit better, okay? Okay, so the other really big and sort of nasty thing to deal with in terms of reflections, which again I think I'd mentioned back in 240, is these so-called via stubs, okay? So the problems with these things, or rather, sorry, I should first define what I mean by stub. So stub just really means that you have some extra piece of transmission line kind of hanging off of your main signal path somewhere. And usually those stubs are kind of completely unterminated, okay? So the reason you typically end up with those things is because of essentially vias. Okay, so in PCBs, when you want to create a via, what you usually end up having to do is basically dig a hole through that entire PCB and then fill it up with copper. Okay, so that means that even if I'm just going, for example, from the top layer down to the lower, just 1 layer beneath it, you still have this huge piece of copper just hanging off of it down on the side. Okay, so what usually ends up happening when you see these things is that in the frequency domain, you get a notch like this. And that just happens because, the signal goes down that stub, reflects off of the open circuit, and comes back. And if you just so happen to hit the frequency at which that's, a 180-degree phase shift, guess what? You get a notch, okay? So especially on, thick backplanes, this is a pretty big culprit, right? Because the thicker your backplane is, the longer that via stub is actually going to be, okay? Yeah.
Case for the backplane designer to actually put the trace at the bottom?
It's a great question. So there's many long and, let's say, heated discussions about that. So if you could put everything on, let's say, the quote-unquote bottom trace, then that may indeed, or rather, make sure that everything is kind of a complete through.
Right.
Then, yeah, that's great. But
obviously,
unfortunately,
you couldn't always, right?
I've got a bazillion of these things, and so some of them are going to be bad somewhere, right? So actually, you asked the great question, which is, well, what can you do by design to make things better? Okay, so I've given you actually a couple of options here. So the first one is, how about we just make the PCB thinner, right? So that stub gets shorter and we push that notch out to higher frequency. So conceptually, great idea. What's the, let's say, minor practical problem? What do you guys think? Why doesn't everyone just make super thin PCBs?
It's not as stiff.
Yeah, it's not as stiff. I've got this 40-inch thing with God knows how much weight on top of it, right? Anything else? Yeah. Say that again?
Some coupling.
There we go. So if I wanted to make it thinner, then of course, oh, you can't see that. Let's try a different color. Okay. Yeah, that's not great either. But basically, if you bring those lines together, right, then you have smaller distance to the ground planes, and of course smaller distance to your other signals too, right? So actually 2 things would happen. All your impedances would go down, and you might actually have more coupling, okay? So it turns out at some point it's actually just physically almost impossible to do that because, you sort of need a certain thickness of copper just to guarantee it actually flows through things sufficiently and etc. So basically, and by the way, as I've sort of pointed out here, usually these things are like 12 layers or so just to be able to actually route all this huge mess of wires everywhere. So kind of tough to really push too much on that dimension. So the other thing that, people will try and do is come up with essentially better vias, okay? So as an example, what people may do is what's called counter boring, where basically after that PCB is manufactured, you kind of know where the thing is roughly supposed to stop, right? So they almost literally just go through that PCB, take a drill, and just drill back on that via so that it just stops right where it's supposed to, okay? Now, you can imagine this is really expensive, right? Because every single one of those vias, somehow you have to drill to exactly the right height. Painful, right? The other thing you can do is what's called these blind vias. So here, this is actually in the manufacturing process. Here, you really will sort of fill in FR4 or resin or whatever you need to get that via to be filled. But now it is, as the name implies, essentially a blind via. So to actually get that to be manufactured correctly, a lot more tricky than actually getting sort of a normal standard via where you can just pour the copper in and then, you know, basically chop everything off on the other side when you're done. Okay? So bottom line is, there's maybe some things you can think of to do, but they're all pretty expensive. Okay? And usually no one wants to pay for it. Okay? So to kind of summarize a little bit what we've been talking about here, what kind of the main message I wanted to get, you know, home to you guys was that this sort of environment that you're going to be working in really does drive very directly the way you're going to end up having to build the circuits around it. Okay? And by the way, I didn't even actually talk about everything because, you know, just a few of these pictures that I'm showing you here, you can imagine building the package for the chip with something that's got 120 gigabit per second IOs or even more than that is pretty tricky. So you have to get all those differential signals out, and oh, by the way, they're not supposed to couple to each other, and oh, by the way, you don't want the package to be all that big, right? So in fact, there's a whole sort of, let's say, subfield of people that essentially just really work on signal integrity, or SI for short. And they'll even do things like, you know, plug into HFSS your chip to package transition, take the whole package, plug that into some field simulator, and so on and so forth. Okay? So again, what this really sort of is getting to is that you need to have an idea of what are the types of channels that you're going to be dealing with so that we can really know why is it that we're building the link circuitry the way we're building it. Okay? And as I've mentioned here, that's really what we're going to be sort of starting to dive into in the next lecture, where we'll start talking about sort of basic transmitter and receiver kind of stuff. But even though, you know, I'm a circuits guy and I like building circuits, the other, let's say, take-home message from this is just don't be a pure circuits weenie. Okay? Because sometimes you'll beat your head over the, you know, against the wall to solve this one really nasty problem where if you just went and actually looked in the backplane and said, why the heck did somebody do that? Why don't I just, you know, shift this line in one particular way, or, you know, make sure these other two things are coupled a little bit better, or, you know, maybe design the package a little bit better and actually have a much bigger impact than just, you know, hacking on the circuit until you're blue in the face. So, any questions on that, or? Okay, great. So I'll see you guys next week.